Good day. Today I will be discussing with you another topic in machine elements. But before that, let us have a quick review of our previous topic about CAM design. So in our previous topic, we discussed about the element of CAM, specifically the CAM terminology, the motion synthesis, and how to draw the CAM profiles. Today I will be discussing with you about rolling contact. This is topic number 8. By the end of this lesson, you should be able to differentiate rolling cylinders and rolling cones, solve problems related to pure rolling contact, and display unity in accomplishing laboratory design activity. This will be the outline of my presentation. Let us start first by defining what is pure rolling contact. So what is pure rolling contact? Pure rolling contact is a motion such that there is a relative motion of two lines or surfaces of which consecutive points or elements of one cone successively come into contact with those of the other in their order. For pure rolling contact, there's no slipping between two surfaces. So we are going to discuss further what does this mean now when we say no slipping. All points in contact have the same linear speed, meaning they have the same velocity. This pure rolling contact has various applications, specifically like wheel rail or tire street contacts, roll bearings, gears, and diverse feeding or transportation mechanisms, which uses pure rolling contact. Two bodies may be rotating on their respective axis so arranged that by pure rolling contact, one may cause the other to turn with an angular speed bearing a definite ratio to the angular speed of the driver. The speed ratio may be constant or variable depending upon the forms of the two bodies. The axis may be parallel axis, intersecting axis, or neither parallel nor intersecting axis. With axes that are neither parallel nor intersecting, the coinciding elements of the rolling bodies may slide on each other in the direction of their length. So since there is already sliding in this motion, this contact is not pure rolling in a straight sense. So parallel axis and intersecting axis can produce pure rolling contact, while non-parallel or non-intersecting axis may produce a sliding effect, which is not a pure rolling contact. So now that we learned about pure rolling contact, let us discuss about rolling cylinders. So what is rolling cylinders? Rolling cylinders can be divided as either external contact or internal contact, as you can see in the presentation. For external contact, the center-to-center distance can be computed as the sum of the radius of two cylinders contacting each other. The center-to-center distance is denoted by the symbol C. The direction of rotation, if they are contacting externally, is opposite. The surface speed of the first cylinder and the second cylinder is the same if there is no slipping with respect to the point of contact. So, because of this, their linear velocity at that point will be the same. Since velocity is defined as 2 pi rn, then 2 pi rn of the first cylinder is equals to 2 pi r1 n1 of the other cylinder. Also, the angular speeds of two cylinders which roll together without slipping are inversely proportional to the radii of the cylinder if we're going to rearrange the previous equation, thus obtaining the ratio that you can see in the presentation. So you can see the relationship between the various variables here in the schematic diagram. So we have shaft 1 wherein the larger cylinder is rotating and shaft 2 where the smaller cylinder is rotating. You can see that the center-to-center distance is just equal to the sum of the radius of each cylinders. Also, you can, if you're going to analyze it, the relationship is that the greater the revolution per minute, the smaller the cylinder diameter will be, because they have inverse relationship with respect to the angular speeds. So therefore, Cylinders which has a smaller diameter can rotate at a larger speed. So that is for rolling cylinders which has external contact. So the linear velocity v is shown here. So this is the velocity at the point of contact. Since the rotation of these cylinders is, as you can see, they are always opposite because the contact, the external contact would produce such effect. Assuming that they are rotating in this direction, as you can see in this presentation, then the direction of the linear velocity at that point of contact would be this red line here. So this velocity is the same for both cylinder 1 and cylinder 2 with respect to the point of contact. And this is the reason why we obtain the relationship that 2 pi rn is equals to 2 pi r1 and 1. So this velocity is constant, and that happened when there is no slipping, meaning there's no slippage that happens at that point of contact. If slipping happened, then the velocities of 1 and 2 will not be the same anymore. On the other hand, for internal contact, the center-to-center distance would be r minus r1. The direction of rotation would be the same because the rotation of the smaller cylinder would compel the larger cylinder to rotate also in the same direction. The surface speed of first cylinder and the second cylinder is the same as with external contact, such that we can obtain the same relationship that you can solve in the previous example. So you can see here in this illustration that indeed the center-to-center distance is equals to the difference between the radius of the larger cylinder minus the radius of the smaller cylinder. Also, we can see here that at the point of contact, the linear velocity would be the same if there is no slippage, thus obtaining the relationship between the angular speed and the radius. So you can see that the same relationship holds true. Therefore, the cylinder which has a larger diameter or radius will rotate at a slower speed as compared to the smaller one. So let us have an example. We have a cylinder 24 inch in diameter of shaft S drives by pure rolling contact another cylinder 2 on shaft T. Shaft S has an angular speed of 600 radians per minute, while shaft T turns 143.25 revolution per minute in the opposite direction from S. Calculate the diameter of the cylinder 2 and the distance between the axes of the shaft. If you can analyze the problem, they rotate in opposite direction, and that can only happen when they are contacting externally. So we draw the illustration that you can see here. We have external contact because they rotate in opposite direction. We do not know the exact rotation, but assuming that they rotate in this direction here, which is opposite each other, we can also see that we can find the relationships based on this figure. So since they roll in opposite direction, the cylinders have external contact. Then we can use the relationship N1 over N2 is equals to R2 over R1, wherein the angular speed is just the inverse of the radius or the diameter of the cylinders. First, we convert the speed of shaft S to revolution per minute so that they have the same dimensions because we are given 600 rad per minute. So convert it to revolution per minute by multiplying it with a conversion factor. 1 revolution is equals to 2 pi rad. So we can now substitute the values to our relationship. Therefore, we can get the radius of the second cylinder, which is 8 inch. And since we are looking for the diameter of cylinder 2, we multiply it at 2 by 2. Then we obtain the diameter of the cylinder 2 as 16 inch. Now that we have the diameter, then we can use the relationship for the distance between the axis of the shaft for the external contact rolling cylinders, which is just the sum of the radius. So therefore, the center-to-center distance, or the distance between the axis of the shaft S and T, or the axis of the cylinders rotating, is 20 inch. So this can be helpful when you say, for example, later on, you will be designing two pulleys or designing gears which are contacting each other, and when you are concerned with the center to center distance so that it can be accommodated by the size of the machine, for example, then you might have to compute the center to center distance or the diameter of each of the cylinders. So this is for external contact. Let us have another example. Two parallel shafts 24 inches apart and having speed ratio of 3 are connected by cylinders in pure rolling contact. Determine the diameters of the cylinders when they turn in opposite directions and when they turn in the same direction. So for cylinders rotating in opposite direction, we can use the same figure that we have in example number 1. So for rolling cylinders which has external contact, since they are in opposite direction, we can use the same relationship, and the speed ratio is given as 3. The speed ratio is just the ratio of the speed of the cylinder which is rotating at a higher speed divided by the speed of the cylinder rotating at a slower speed. So basically in our illustration, since R2 is the smaller cylinder, then it is the the cylinder which is also rotating at a higher speed. Therefore, we can have this relationship n2 over n1 is equals to 3. Again, since r2 is smaller in diameter, then its speed would be larger than the speed of r1. So therefore, our speed ratio is n2 over n1 is equals to 3. And if we're going to substitute that in the relationship that we have in terms of the angular speed and the radius, then we can have the inverse of that n2 over n1 as equals to our n1 over n2, which is equals to r2 over r1. If you're going to rearrange that, then we can get r1 is equals to 3 r2, or the radius of 1 is equals to 3 times the radius of 2. So the distance between the axis of the shaft is 24 inch. And using our relationship between the distance between the radius, if they are in opposite direction or external contact, 24 inch would be equals to r1 plus r2. Since we already know the value of r1 in terms of r2, then we can substitute that one in our previous equation, thus obtaining the radius of 2. Since we're looking for the diameter of cylinders, then the cylinder 2 would have diameter of 12 inch. So 12 inch would be the diameter of cylinder 2. And since the cylinder 1 has a radius 3 times of that of cylinder 2, therefore we can get also the diameter of cylinder 1 as 36 inch. So we have the diameters of cylinder 1 as 36 inch and the diameter of cylinder 2 as 12 inch. And these values coincide also with our figure that you can see on the presentation. Now that we're done solving the diameters of the cylinder when they turn in opposite direction, let us try to examine now when they turn in the same direction. So take note that you can see here that the diameters are 12 inch and 36 inch respectively. Let us see if the diameter would increase or decrease if they would turn in the same direction. So for cylinders rotating in the same direction, so for the same example, when they turn in the same direction, we would have this figure that you can see here in the presentation. So we can also still use the relationship between the angular speed and the radius, even though they are in internal contact. The speed ratio is 3. If we're going to examine it, n1 would rotate at a larger speed. So therefore, our ratio n2 over n1 would be equals to 1/3. Since n2 would have a slower speed as compared to n1. Substituting these values in our relationship between the angular speed and the radius, then we can get r2 as equals to 3 r1. Also, using the relationship between the center distance, which is 24 inch, that would be equal to r2 minus r1. Substituting the values of r2, then we can get the value of r1 as 12 inch. So the diameter is 24 inch. Now that we already have the radius, then we can get the radius of r2. The radius r2 would be equals to 72 inch. So you can see that if the same cylinders, if the same example, would be rotated in the same direction. If they have internal contact, it would require a larger uh, gears, for example, or pulley or cylinders, as you can see here in this example. So now that we're done examining the relationship in the rolling cylinders, let us examine now the relationships with rolling cones. Some example of rolling cones are the miter gears and also the bevel gears. So if you're going to extend the center connection between these cones, for cones rolling together without slipping, as you can see here in the presentation, so we have here the schematic diagram of rolling cones. Say for example, you have this figure that you can see here, wherein our radius of the first cone would be R and the radius of the second cone would be R1. The second cone is rotating at a speed of N1 while the first cone is rotating at a speed of N. The shaft angle, which is denoted by the angle theta, is the angle between the shaft of these two cones that you can see here. Alpha here would represent the cone angle of the first cone, and beta would represent the cone angle of the second cone. For rolling cones without slipping, the angular speed of two cones which roll together without slipping would be inversely proportional to the radii of the cylinders. This is just the same as that of a rolling cylinder, if you can remember. If we are going to examine the figure, we can see that R1 and R2 can be expressed in terms of sine beta and sine alpha respectively. So you can see that the relationship is that the angular speed can just be written in such a way that they would be inversely proportional to the sines of the angles, which are the cone angles. So again, the angle alpha is the cone or center angle of cone A, and beta is the cone angle of B. The angle theta is the angle between the shaft or the shaft angle. If it is assumed that the sense of direction is the sense in which a given shaft is seen to be rotating as one looks like the shaft toward the intersection of the axis, then there would be two cases. They could rotate in the opposite sense of direction of the shaft or same sense of rotation as that of the shaft. So let us try to examine them. So two cones may roll in external contact or internal contact, the same as that of a rolling cylinder. Internal or external contact doesn't mean opposite sense of rotation or same sense of direction. The kind of contact, whether external or internal, would be dependent on the combination of the angle between the shaft, the sense relation, as well as the speed ratio. So here we would be examining it whether they would have external and internal contact depending on the angle theta, the cone angles, as well as speed ratio. It is not the same as that of a rolling cylinder wherein the contact would be dependent on the rotation, whether they have opposite sense or same sense of rotation. So here it would not be the case. So for rolling cones with opposite direction of rotation, say for example you have here a schematic diagram where A here represents the shaft of cone A and B represents the shaft of cone B, and since they are rotating in opposite direction, as you can see here, NA is rotating counterclockwise and then NB is rotating counterclockwise, then for this relationship, if you can see here, this would be the corresponding cones. So the tan beta can be computed as sine theta over n bet, the speed of beta, the speed of shaft or cone B, or the shaft of cone B divided by the speed of the shaft of cone A plus cosine theta. And also we can also get the tan of alpha using another relationship. So this formula that you can see here in the presentation is already a derived formula. So you can use this whenever you have rolling cones with rotation opposite each other. So you can also see here that RA and RB So this RA would represent the radius of cone A, RB is the radius of cone B. And for rolling cones which rotate in the same sense of direction, as you can see here in this diagram, so this would be the schematic diagram if that would be the case. You can see here that their diameters or radius would uh, interact each other, as you can see here. So we can also get the relationship between the different angles here using this formula. This is a derived formula that you can use whenever you have rolling cones which are rotating in the same direction of rotation. You can also examine here that our theta uh, the would be smaller than the value of alpha, as you can see here in this diagram. And then the the angle would have a relationship in such a way that our uh, theta would be the difference of alpha and beta. So let us have an example. So shaft A turns 100 revolution per minute and shaft B rotates 150 revolution per minute as shown. They are connected by rolling cones. Calculate the cone angle of each cone. If the base of cone on E is 3 inches from the vertex, calculate the diameters of both cones. So this is the illustration that you can see. We have the shaft A and shaft B of cone A and B respectively. And we're also given here the speed, which are rotating in opposite direction, as you can see here in this figure. And the shaft angle, or the angle between the shaft, is 60 degrees, which is the value theta. If we're going to draw the schematic diagram of that cone, this would how it would look like. So this 3-inch here is the distance from the vertex, which is the intersection of this of their shaft axis, to the base, which is perpendicular to the base of cone A that you can see here. So that is 3 inches. So we would solve for the diameters of both cones. So for rolling cones, we can have the relationship NA over NB is equals to RB over RA. So they are just the inverse of each other. If we're going to examine the figure, our A has a smaller speed and B has a larger speed. So this is the reason why A here would be a cone in terms of diameter, because it is rotating at a smaller speed if you're going to base it on the relationship which is inverse of each other. Substituting the value of NA and NB, then we can get the relationship for RA with respect to B. So RA, the radius of cone A, would be equals to 1.5 times the radius of cone B. So you can see that RA would be larger than cone B. So from the figure also, if you're going to use trigonometry, you can get that tan alpha is equals to RA over 3, based on the triangle that you can form here with respect to the cone A, its radius, and this distance from its vertex to the base, as well as this alpha. So tan alpha would be opposite, which is RA, over the adjacent, which is 3 inch. So for rolling cones with opposite direction of rotation, we can use the formula that we have in the previous slide. So that tan alpha is equal to sine theta over NA over NB plus cosine beta. Substituting the value that we know from the given, we can get tan alpha 0.7423. Therefore, we can get the value of the cone angle of cone E, which is 36.6 degrees. So therefore, the cone angle of A is 36.6 degrees. Also, based on the figure, our sum of the cone angle is equal to the shaft angle. So since we already have the value of the alpha, then we can get the beta also. So beta would be 23.4 degrees, and that is the cone angle of cone B. So from previous result, we know that tan alpha is RA over 3. Rearranging that, we can get RA is equal to 3 tan alpha. Since we already have the value of alpha, then we can get the value of RA. RA would be 2.228 inch. Since we already have RA, then we can get the diameter of cone A as 4.46 inch. So the diameter of cone A is 4.46 inch. The diameter of cone A is 4.46 inch, and we're going to use that later on when we calculate for the value of the diameter of cone B. Now, uh, if we're going to look again our diagram, we can get here this line X that is denoted by this red line here. So this is representing the element of contact. So this is the point of contact of cone A and cone B. So it is a line. So that is the element of contact denoted by X. So we need to solve that value in order to get the radius of uh, cone B if you're going to look at the figure. Because this angle here would be 90 degrees. Therefore, it would be the hypotenuse of this angle here with respect to beta. So that we can get RB. So using Pythagorean relationship of cone A of this triangle here, our square root of r squared plus the square root of ra of 3 squared and ra squared would be equals to 3.7368 inch. So this is just a Pythagorean relationship of this triangle here in order to solve for the element of contact x. So now that we have the value of that, if you're going to look at the triangle here that we can form in the cone B, we can get another right triangle wherein x would be the hypotenuse, RB would be the angle opposite of beta. So using the relationship, we can get RB as x sine beta. Since we already have beta and x, then we can get the radius of cone B. So the radius of cone B is for 1.484 inch. And for the diameter of cone B, that would be twice of that, that is 2.968 inch. So the diameter of cone B is 2.968 inch. So now that we already have the value of the cone angle as well as the diameter of the cones, then we can draw a more precise and accurate diagram of this rolling cones in contact. So this is when they are turning in opposite direction. So let us have another example wherein the cone would rotate in the same direction that you can see here in the presentation. So we have shaft A rotating at 300 RPM and we have shaft B rotating at 100 RPM. The shaft angle is 30 degrees. You can also notice that A is rotating at a larger speed, therefore its diameter would be smaller. So that's why when you draw the diagram, we would have it as a smaller cone that you can see here. So unlike our previous example, our cone angle of A would be denoted by beta, and then our cone angle of B would be alpha. So the distance between the vertex and to the base of cone B as given in the problem is 2 inch. So that's why we have here 2 inch. So for rolling cones with the same direction of rotation, we can use the relationship tan alpha is equal to sine theta over cosine theta minus NB over NA. Substituting the value from the given, we can get the value of alpha as 43.18 degrees. Since we know that alpha minus 30 degrees is equals to beta, then the cone angle of, so this would be the cone angle of B. So this is 43.18 degrees. So based on the figure, alpha minus beta is 30 degrees. Therefore, we can get beta as the difference between alpha and 30 degrees. So that is 13.18 degrees, which also coincides here in our figure since beta is a smaller angle here and alpha is the larger angle. So the cone angle of A is 13.18 degrees. So now that we have the cone angle, we can solve the diameter also. So based on the figure, our tan alpha is equals to RB over 2 inch by tangent. So since tangent of alpha is opposite, which is RB, divided by adjacent, which is 2 inch. Therefore, we can get RB by substituting the value of alpha. So RB is 1.876 inch and the diameter of B would be 3.75 inch. The diameter of cone B therefore is 3.75 inch. So the element of contact X is the line wherein these two cones are contacting each other. So this would be this line here that is pointed by the cursor of this mouse. So this is the line. This is the element of contact X. So if we're going to analyze the figure, we can get the element of contact X by using a Pythagorean relationship between the radius of B and the value 2 here. And that is equals to 2.742 inch by using the Pythagorean relationship. So the element of contact X or the line of contact is 2.742 inch. So again, this is the line of contact of the two cones. So based on the figure, since we already have the value of X, then we can get the value of RA as X sine beta. Since we can see here that sine beta is equals to opposite, which is RA, divided by the hypotenuse, which is the line of contact. So that's why we have RA is equals to X sine beta. Substituting the values, then we can get the value of diameter of A as 1.25 inch. So the diameter of cone A is 1.25 inch. So now that we already have the diameter, then we can also draw it more accurately. So again, this is the line of contact. It's denoted by the symbol X. So if you are going to examine, solving rolling cones would require us first to use the relationship between the angular speed and the radius. And sometimes it would we would have to use trigonometric formula, the trigonometric ratios, in order to get the length of the different quantities that are related to each other. We can use the Pythagorean theorem, Pythagorean relationship, and among other formula in order to solve the different unknowns in the problem. As a summary, we were able to discuss what is pure rolling contact and the two types, which is rolling cylinders and rolling cones. See you in our synchronous discussion.